Today we're going to work towards proving a new basic fact about natural numbers that we couldn't prove last week, namely that addition is symmetrical in its two inputs. So we're going to prove a plus b equals b plus a. So doing this proof needs two new bits of technology, so the real purpose of this video is to introduce those. The first new thing is that we can have helper proofs, just like we can have helper functions in programming. Namely, everything that we've already finished proving becomes available as a given in later proofs. So we can use this to prove some things from the first 2 weeks in new ways. So here's the simplest thing I could do. For example, I could say prove P implies P by imp I. And then if I want to prove P implies P a second time, I have the option of saying given. So this only works this way round. If I try to do it the other way round, it won't work. So the real proof has to come first. And another thing that you can do is the earlier proof can be incomplete, so it can contain a question mark. Now, if you send this, ask will do something a bit subtle. If you look at its response for this second proof, this proof has been accepted because it contains no remaining question marks, but the proof has not changed to proven. So previously this was impossible. Previously, proof would change to proven exactly when there was no question marks left. But now it's detecting that this proof is depending on an earlier incomplete proof, so it can't be 100% certain that this is actually true. So if I now complete the earlier proof by adding back in by imp I, then the second proof will change from proof to proven, like this. Okay, now that's a very basic example. I'll show you something more interesting that you can do with this. So here is the proof from week 2 exploration 2 of P or not P using by contradiction. And I'm going to show you a new proof of the formula prove P implies Q implies not P or Q. This was an exercise in the week 2 exercises. I'm going to use by imp I, and now I'm going to say from P or not P. Now remember, I told you it's almost always a good idea to use from followed by a formula that you have given. And here, P or not P is now given because we proved it in an earlier proof. Now, when I send this, we are doing from on an or formula. So it's going to split into two branches, one where P is true and one where not P is true. So this allows us to essentially case split our proof into the possibility that P is true, in which case we're given P, and the possibility where P is false, in which case we're given not P. So this is a very powerful proof technique. So I will just quickly finish this proof for you. So in the second branch, we're given not P, and we want to prove not P or Q. So this is easy. I can do it by or introduction on the left. And in the second one, in the first branch, we're given P, but we also have a P implies Q sitting around. So I can try to prove Q. So I'm going to say by or introduction on the right to say that I want to try to prove Q. And then I can say prove Q from P implies Q to complete that proof. Okay, so what does this have to do with this week's topic? Well, previously we didn't need this feature. We could always get by without it. But for proving equations about programs, these helper proofs are really useful. So let's get started on our proof of A plus B equals B plus A. I'm going to say inductively A, so we'll do induction, proof by induction on A. And then I'm going to say from A to split into the case where A is 0 or A is a successor. So this is an example where ask has not been able to solve our base case by itself. So if you look at the thing that we now need to prove in the base case, this is 0 plus b equals b plus 0. This might look a bit familiar because this was actually an exercise in week 6. So what I'm going to do is I'm going to add this as a helper proof by saying prove 0 plus n equals n plus 0, question mark. And now here in my main proof, I'm going to say given. And what you'll notice is I've changed the names here. So given is smart enough to know that this matches this up to some renaming. So this is exactly the same as when you do a function call, the name of an input from the function's perspective can be different to the name of an input from the caller's perspective. So at the point where you do a function call, the point where you call a helper function or the point where you call a helper proof, you are allowed to rename some variables. I will just, you've seen this proof before, so I'll quickly fill it in. I say inductively n and then from n, and then this time ask will be able to solve the base case itself, and it will stay invisible, and I'll keep it invisible this time. And the inductive step works by tested, and there's another invisible line that I will also leave invisible because you've seen it before. Okay, so this finishes off our base case of our main proof. Now, in the other branch, I can make a little bit of progress by writing tested to tell ask to try to simplify both sides. So when I send this, ask will send back a new goal where, so the right-hand side hasn't changed because ask wasn't able to simplify it, but the left-hand thing has changed a bit. Now, okay, so now to make progress from here, we need another new piece of syntax. So if we want to prove an equation, we have another way we can do it, which is to prove that both sides are equal to some third thing. So let me show you this in isolation. If I bring some A, B, and C into scope, I can say prove A equals C by root B. So this is a new piece of syntax, which is saying that I'm going to try to prove A equals C by proving that each side individually is equal to B. So when I send this, ask will give me two sub-goals, one that's prove A equals B and one that's prove B equals C. So if you think about it, if you know that A equals B and you know that B equals C, then you know that A equals C. The difficulty here is that this B came out of nowhere. It doesn't appear in the thing that we want to prove. So it turns out that in this case here, I want to say by root S B plus A prime, and you need an extra pair of brackets than what you need. Sorry, an extra pair of brackets than what you might think you need. So here's the thing. This expression, SB plus A prime, I kind of pulled out of a hat. I had to do some kind of hard thinking to figure out what this would have to be to make this proof work. In general, coming up with these is very difficult. Also, coming up with helper proofs is very difficult. So I will never ask you to invent your own helper proofs. I will always give you the helper proofs that you will need as sub-questions. Similarly, for these, by root, I'm hoping to be able to design questions so that I can tell you this as a hint without giving the entire question away. Because coming up with these sometimes is a creative leap. Okay, now here's the thing. Even after a new piece of syntax and a creative leap, this proof still is not done with us. This is a very difficult proof. So we have two different subgoals now. One is invisible and one is visible. And they each contain a different subtlety. So I'll deal with the visible one first. So in the visible one, it turns out to be useful to write a helper proof as well. The helper proof that we need here is something like prove m plus sn equals s of m plus n. So if I say given here, hopefully this works. Yes. So again, this is a renaming of some variables, plus the equation goes the other way around. I've turned this equation backwards. So this side matches this side, and this side matches this side. So given is also smart enough to be able to try all the equations backwards. Okay, now this proof here, this is another easy one. I can say inductively m, where prove plus sn equals sn plus n from m. And now, again, ask will solve the base case by itself. And the other one goes through by tested. Okay, so at this point, ask has accepted this proof, but I also want to talk about the invisible branch here, which contains a different subtlety. So if you think about it, we are trying to prove this s a prime plus b equals b plus s a prime by root this thing. So this is the second half where we're proving that this equals the right-hand side. So you would think that the left-hand side sub-goal would be prove s a prime plus b equals s b plus a prime. So prove that the left-hand side equals the thing we're going by root of. But it turns out, slightly mysteriously, this doesn't work. The reason is that for slightly technical reasons, ask really hates it when you say an equation where both sides begin with the same constructor. So what you need to do here is remove the s from both sides. And now if you look, so now ask will accept this. Yeah. And now if you look at this, the thing that we need to prove, this is exactly our inductive hypothesis. This is a plus b equals b plus a, but with a replaced with a prime, which is a minus 1. So this is our inductive hypothesis, so we can get it by given. And this is the complete proof that the inputs of plus are symmetric. This is a difficult proof. This is a significant difficulty spike compared to everything that you've seen so far. Okay, so there is a couple of more features in ask for proving things about equations, and they will be the topic of exploration 3.